Okay, this is your textbook. Chapter 3 is related to our weekly material for today. It's about nuclear medicine, aspect of medical imaging techniques, and 3 different modalities are being taught in the chapter. So-called planar scintigraphy. Scintigraphy is the usual clinical name for nuclear imaging technique. Single photon emission tomography, so it's nuclear imaging computed tomography techniques, so slice imaging, and a modality which combines positron emission tomography and CT together. Okay, so what you have learned in the previous section is all related to planar scintigraphy. SPECT and PET CT will be the issues for this section. So there's a big reading for introduction. So let's read very fast. The agent in important thing is agents accumulate in specific organs. Okay, agent means radioactive substance. There are 3 different modalities under general umbrella of nuclear medicine. The most basic one is planar scintigraphy, topic of session 1, and it's very analogous to X-ray scan, gives an image of in 2 dimensions. Good for screening tumors, meta tumors, etc. The most well-known pharmaceutical is technetium-99 meta. Okay, this is a special kind of heavy nucleus. This is radioactive. So in the nucleus, that atomic weight 99 is very unstable. And it emits gamma rays at 140 kiloelectron volt. Okay. So basically what we have learned in the previous hour was related to PET, positron emission tomography. In positron, annihilation produces gamma rays of 511 keV. In other types of planar nuclear medicine, when you use technetium-99 for some specific investigations of, let's say, thyroid gland on the neck, etc., their gamma ray energy is 140 keV. This is one of the lowest ones, okay? You remember X-ray imaging techniques are up to from 20 keV to say 150 keV, but not in clinical environment. So this is the lowest energy range of nuclear medicine, which is highest for conventional X-rays. The second type of scan is single photon emission computed tomography or SPECT. This produces a series of contiguous 2-dimensional images of the distribution of radio tracer using the same agents as planar. Compared to planar one, SPECT is tomographic, which is volumetric kind of. So CT, as the name implies, X-ray CT and SPECT CT, SPECT are very analogous. They are rotating, their detectors are rotating and obtaining volumetric data. And in the previous session, we have learned PET, which creates 2 gamma rays, 511 keV, and PET CT. And the last scanner combines these 2, PET and CT scanners together. There are some numbers of United States medical systems, etc. Some data for population, some percentages, etc., etc. We are missing this. So this is a kind of a basic block diagram, what's going on. So first, a radio tracer injected into the patient, sometimes swallowing, sometimes inhaling, but this technetium is being injected, and patients start to form gamma rays of this energy. Scintillation crystal receives crystal sodium iodide and converts gamma ray to many light photons. Note that this is high energetic. This is high energy part. This is low energy or visible light part. So theoretically, you can, from one gamma ray, you can produce thousands of visible light rays with blurring, etc. Photomultiplier tubes receive these light, position network locates XY coordinate, pulse height analyzer analyzes the intensity of the pulse, and the accepted ones are added to be displayed in the image. Here is a sample image of the head after a SPECT technique. You see the boundaries, you cannot resolve the organs, etc. But these shades of white and gray or dark gray, etc., gives very valuable information to the doctors about the physiology or operation of the tissues or organs. So this is the system. The system consists of some kind of physical quantities related to radioactivity and half-life. So this is the governing equation of the charge accumulation is, the number of decays is proportional to the net time rate of change of the concentration, and equal to the, that's also equal to the concentration with a constant lambda. Here lambda is the parameter which is related to the half time or time constant. So this equation is a first degree differential equation, very similar to resistor capacitor networks or resistor inductor networks of voltage and current respectively. So this is the same. So that's the reason we have the same number of decays equals to number of decays at t equals to 0 with exponential decay constant, okay? So what you have learned as tau before is lambda in this course and in this book. So this is a kind of graph showing half-lives, etc. So here the book denotes it as tau half. So number of decays drops to 1/2 of its value in half time. Again, if the same half-life elapses, actually this is not to, this figure is not drawn to scale. These intervals should be equal, okay, as the parameter indicates. Anyway, it drops to its half of its value. Actually, theoretically, you can never reach 0, but for the explanation in the mathematical terms, this is it. So half-life and lambda or tau, time constant. What was time constant in electronics? That's the value of power is less than 3 decibels if of the incident or reference power. But it's not half, it's 70%. Okay. So there's a relationship between half-life and time constant with that ln2. You can derive this equation by substituting these variables into the main equation. So I leave it as an exercise. This is the main equation. And effective half-life is defined as the interaction between biological biological half-life and physical or material half-life. So that's a general conclusion. Effective half-life is less than the shorter of the two half-lives, material half-lives and biological half-lives. So there's an example and solution. This is left as an exercise. We are continuing. Properties of radiotracers for nuclear medicine is related to some chemistry and physics. So ideal properties of radiotracer for planar scintigraph and SPECT include a half-life that's short enough to produce significant radioactivity without requiring very large initial dose. Okay, so that to save the patient, of course. Decay should be via emission of monoenergetic X-ray without emission of alpha or beta particles, because alpha is another particle which is a very dangerous thing to the body. Beta is unwanted energetic things. X-rays, sorry, gamma ray should be greater than 100 keV so that reasonable proportion of X-rays which are emitted deep into the tissue have sufficient energy to travel through the body and reach the detector. Okay. Energy of gamma ray should be less than 200 keV so that rays do not penetrate thin lead septa in collimator, which is analogous to anti-scatter grade. Okay. Radio tracers should have a high uptake in the organ of interest. This is also important. And these are pharmaceutical research areas. Most widely used radio tracers, 99M technetium, 90% of planar scintigraphy of the SPECT tissues, studies, etc. So that's a nuclear reaction of nuclear decay reaction of this thing. We will not go into deep these kind of chemical or nuclear equations. We are related or interested in only gamma in this course. And these are nuclear things or atomic quantum levels of what's going on over there. Technetium generator is the instrument who produces technetium at some other industrial factory. Okay, so technetium is generated over there with very tight controlled procedures. Then they are packed into let's say boxes and transferred to the hospitals or investigation or imaging environments. So these are the elements used as radio tracers, similar to technetium, 67 gallium, 201 thallium, etc., xenon are also used with those kilo electron volt energy ranges. And clinical applications, various or tumor detection or myocardial or heart viability, lung vent inflammation, etc., are their potential usages. You see, they're also half-life in hours are also listed. The shortest one is the technetium. So this is a generator administering thing. You have to send neutrons to the physical sample, etc. We are not interested in this course. So if you are interested to learn more about nuclear activities, you can read those pages. So there are some solutions about nuclear activities, obtaining tracers, etc. Distribution of technetium-based radio tracers within the body. So this is again related to chemical or physical things. How do you perform or produce these things from different chemical compounds, doing what kind of procedures, utilizing some things, etc., which is left as an exercise. Here's our topic of interest, gamma camera. It's shown in figure 3.5 is instrumental basis for both planar scintigraphy and SPECT with the resource one. Patient lies on a bed, position, the camera is positioned close to the organ of interest. Gamma camera must be capable of gamma ray detection rate up to tens of thousands per second. So tens of thousands photons per second should be received, and associated electronics should be fast enough to count them. Okay, that's the first constraint of it. And should reject those gamma rays that have been scattered in the body. You remember, if the photon is scattered in the body, it loses its energy and the direction information, so it's invaluable for imaging. So therefore, it should be rejected. So rejection means there's a kind of comparator circuit, analog or digital decision algorithm to test its energy and test within the limits to decide whether useful or not. Collimator is a special instrument. It's the first major apparatus to absorb, okay, undesired scattered rays coming oblique towards the photomultiplier tubes. So after collimator, we have a circular disc, usually 10 millimeters, 12 millimeters thick of a very pure, good sodium iodide crystal. And photomultiplier tubes are located on top of them. So each tube has 4 outputs, or in a matrix location, you can determine its horizontal and vertical directions with associated electronics. So this, together with the high attenuation of gamma rays within the body, leads to a very high proportion of emitted gamma rays, 99.9% or more, not being detected. There are 6 basic collimator designs: parallel hole, slant hole, converging, diverging, fan beam, pinhole. Those are designs of collimators, okay, related to collimators. We have not gone through the details of collimator design. Okay. Signal to noise ratio and contrast to noise ratio should be maximized. That's the reason of collimators. So some basics about parallel hole collimators. Parallel hole collimator has some kind. Okay, where is the, yeah. The collimator has a kind of, let's say, rectangular thick or field region and air region, so that that special aperture rays can travel through, but other parts are absorbed, and their thickness and the distance between the structure are some parameters. Similar to parallel, slant hole, converging and diverging kind of collimators are also possible or utilized in special investigation. You can imagine or guess that this is for smaller organs, and their, let's say, concentrated gamma rays are imaged to a larger imaging field of view. And this is the reverse. It's, the organ is very big and the image can be concentrated, smaller. And this is, let's say, if some kind of oblique rays are desired, analogous to parallel, but in a different angle. So those are the best for the application, clinical application. So there are some design criteria, definition of dimensions, separation of lead strips, values of some parameters about the quality of them, etc. I have not gone through it, and those are in the science of collimator design. So that's enough for the collimator. So this is the first instrument or first part located in the front of the gamma camera. The next, detector, scintillation crystal, and coupled photomultiplier tubes. Detector scintillation crystal is basically iodine. Iodine is a big molecule that captures X and gamma rays. Sodium iodide is a good, appropriate, industrial, not so expensive, and it can be easily produced in the big crystal in decades, many decades, still being used. This is approximately 40. So gamma ray is not detonated in the detector using crystal, which converts their energy into light. In the gamma detector is a large single crystal of thallium activated sodium iodide. So its chemical component. So it's 40 to 50 centimeter diameter, big circle or cylinder. And the thickness is not written. Probably it's 1 to 1.2 centimeters. Anyway, it depends, of course. When gamma ray strikes the crystal, it loses energy through photoelectric and compton interactions. We have seen these interactions in the previous week's lectures related to X-rays and X-ray tissue interaction, which it's the same in gamma rays as well. Excited electronic states within the crystal, the excitation of these states in roughly 230 nanosecond later via emission of photons. So that means if the gamma ray photon interacts with the crystal electron, it's makes the energy of an electron higher to jump to a higher band, and after 200 and so nanoseconds, it returns back. So emitting exact energy gamma as gamma ray to the detector. Okay. So the wavelength of this emission is around 450 nanometer, which is a visible blue light, because that sodium iodide crystal atom valence electrons at the end, when they return back, they emit blue light, but many blue lights for the X-ray photon. So gamma ray or X-ray photon hitting to a surface creates that visible blue light photon around after 200 nanoseconds or so. That corresponds to the photon energy of around 4 electron volts. A very important characteristic of scintillators, such as this one, amount of light, number of photons produced, is directly proportional to the energy of X-ray. So this is one of the most important things. We have to produce visible light photons proportional to the incoming gamma ray photons. This is the intensity of the imaging, let's say, gamma ray. So, and also proportional to the number of X-rays coming from the organ. Sodium iodide is chosen for a number of reasons. It has high linear attenuation coefficient, so capture efficiency is high. One light photon produced 30 electron volt energy absorbed, an efficiency of around 15%, which is more than the other substances. It's transparent to its own light emission at 450 nanometers, so little energy is lost due to absorption, which is good. It's efficient. Large circular rectangular crystals can be grown easily, so this is one of the most important industrial property. And inexpensively, which is very desired. That emission wavelength is well matched to the optimal performance of the conventional photomultiplier tubes. So photomultiplier tubes are visible light sensitive, and they are really good, have their matching for the blue light instead of red light, etc. So that's another good choice for the action, scintillation action. The only disadvantage of this is hygroscopic. It absorbs water, so it should be hermetically sealed. So that means that crystal, it's covered with some kind of seal material so that water, vapor, etc. cannot penetrate in. Otherwise, that crystal will lose its property in the long run. Therefore, also making quite mechanically fragile. So that's another weak point of the crystal. Well, as you know, nothing in the nature is purely perfect. Everything has advantages as well as disadvantages, like sodium iodide crystal as well. Thickness of the crystal involves the same trade-off between spatial resolution and sensitivity of a detector in planar X-ray imaging. Thicker the crystal, the broader is the light spread function. Also, you can think of its line spread function, and lower the spatial resolution. You remember you have done line spread function in your homework number 1, finding the Gaussian, etc. Broader means full width half maximum value is greater, which is not good for detecting two very close objects. But the greater the number of X-ray detectors and higher the SNR. So you have to be thin also for sharpness, and you have to be thick for detection efficiency. There's a trade-off. For imaging, optimal thickness is around 6 millimeters. However, although lowest major scans use 99 source radio tracer, etc. Usually 1 centimeter is generally used. Okay, so between 6 millimeter and 10 millimeter is the optimal choice. There also exists 12 millimeter crystals, but you can imagine those are those do have big blurring compared to these two. They are produced commercially for gamma cameras, a steep drop-off in the value move as a function for such crystals, etc. PMT devices. Okay, so enough for the crystal. Now comes for the photomultiplier tubes. The basic design of photomultiplier tube is given in 3.8. So this is, first of all, let's show, this is the structure of sodium iodide crystal. Okay, cylindrical or rectangular or piece. So those look like a opaque plastic material, and their mass attenuation coefficient with respect to energies are, as shown, exponentially decreasing. So for technetium 140 keV, we are here. For PET, we are around here. Okay, so you have to consider the energy of the gamma ray photon. Photomultiplier tube is the next topic, shown in 3.8. We are looking for 3.8. Okay, here is the photomultiplier tube. There's a crystal at one side, and the photon coming to the crystal. Okay, there's a vacuum in it, so the tube is like this. Okay, this side is up now, and electronics and electrical connections are down. They are up. There are metallic varying high voltage plates in there. So electrons coming towards the crystal to the top, you see the circular region, they produce, okay, gamma rays or light photons coming to the crystal are photoelectrically transformed to electrons. This is the energy equation inside. The electrons attracted by the positive voltage, they hit the plate and produce more electrons. They are also attracted to another higher voltage, and they produce more electrons with the hitting, because during the acceleration, like X-ray tubes, their energy is increased. So from 1, we have 10, maybe 100, maybe 1,000, etc. It's geometrically increasing. The number of electrons here and there are proportional. So this is like an optical or number of electronical amplifier. So this is called the photomultiplier tube. It has different voltages, high voltages, positive voltages, and these are the terminals. And of course, there may be a filament to produce free electrons, etc. And there are some, at the end of the stage, there's a kind of electron counter or a current meter, ammeter. So their terminals are down by the photomultiplier tube ends. Okay. So there's an example. Since there's a solution, I left it as an exercise for you. And these photomultiplier tubes count the number of electrons, or actually photons, coming to their views. And from all position of the photomultiplier tubes, with the position networks, their XY coordinates can be calculated. Pulse height analyzers decide the energy level of each pulse, whether that pulse is a valuable information for the image or not. Okay. So whenever a scintillation event occurs in sodium iodide crystal and the photomultiplier tube closest to the scintillation event produces the largest output current. If this were only method of signal localization, then the spatial resolution would be no finer than dimensions of photomultiplier tube, several centimeters. Each tube, as the book said, has a diameter of several centimeters. But adjacent PMTs produce smaller output currents, which the amount of light detected being approximately inversely proportional to distance between scintillation events and the particular PMT by comparing the magnitude of the currents from all PMTs. The location of the scintillation within crystal can much better be estimated. In analog gamma cameras, this process is carried out using an Anger logic circuit, which consists of 4 resistors connected to the output of each PMT. Actually, as shown in figure 3.9, this network produces 4 output signals, which are summed for all PMTs. The relative magnitudes and size of these sum signals can be defined estimated XY location of the scintillation event in the crystal given by the X coordinate is plus and minus signal difference and summation, and Y is difference of Y signals. Those you can consider this an horizontal and vertical parts from the 2 parts of the photomultiplier tube. But this is rather a little bit old technology. In more recent digital cameras, the currents for all PMTs are stored and position estimation performed using computer algorithms after all the data have been acquired. Correction for non-uniform performance of PMT can be built into digital system. Okay, this is related to old system. Okay, and this is related to height and anxiety. So let me try to search the algorithm because it's not written in the book. We have 6 minutes. Good. Let me try to find it. Where was it? Not this one. Okay. I hope everybody can see this slide. Okay, this is the body. These are the photomultiplier tubes, and each has associated electronics for number of counts coming from that tube. Coming from that tube means visible light photon numbers in that circular area. So assume this is the value of C1 and C2. You have all the numbers. Usually number of photomultipliers may be 19 or 31 or even more. This is the simplest and smallest angle camera of 19 photomultiplier tube. So we have 19 variables after a scintillation. Scintillation point is here, right where the cursor is placed, and it has a circular variation. You see, big portion is in that circle, a very small and relatively larger portion is here. You calculate the number of counts there, and the number of counts is proportional to the area under this individual PMT tube. So exact coordinates in 2 dimensions equal to the relative number of counts times the coordinate of the center of each tube, r of xi, yi, divided by total number of counts from all tubes. So this is like calculating the center of mass equation in physics, okay? So from all counts from all tubes, you can calculate x and y coordinates of each scintillation point. That's the reason if we have considered only this tube, then we would mark the center of the tube as the scintillation event point. But if we consider all the tubes, then we can accurately find by using this equation. So let me add this. Let me get maybe this could be an idea. Let me share with this with you guys.
Hocam süre dolmak üzere sanırım.
Tamam. Kesilirse sorun değil. Yine saat başında toplanacağız. Okay, there's no problem about breaking. If it starts or stops instantly, we will start our new session at 17 hours.
20 saniye falan var hocam.
Biliyorum, görüyorum.